All right, welcome to section 13.7 on tangent planes and linear approximation. In this intro video, I just want to recall a few things from Calc 1 regarding linear approximation, and this is going to serve as good motivation for everything we're going to see in this section. All right, so let's say we have a function of a single variable, y equals f of x here, and we're interested in the behavior of this function near a point when x is equal to a, right? So here we are at the point a comma f of a. And let's suppose that our function is differentiable at the point x equals a. So what does that mean again? Well, if a function is differentiable, then the graph of our function will look linear near this point a comma f of a. So in other words, if I say zoom in really close to this point, okay, even though my curve, well, curves, right, nearby this point, this thing is going to look extremely straight. Okay, so what would be an example of something that was, say, not differentiable at a point? So not differentiable might look something like this. You have a sharp cusp here in your graph. So the deal here is that at this cusp, no matter what scale you're on, right, this thing is never going to smooth out, so to speak, okay? So that would be something not differentiable. Now, we will always make the assumption that the functions we're dealing with and the points we're considering, we do have differentiability, okay? So keep that in mind. All right, so now let's go ahead and look at, right, a line that this graph in yellow is going to look like upon zooming in, right? And so I'm going to call this thing the linear approximation of our function f at x equals a. And what is it? Well, it's simply the tangent line to our curve at this point a comma f of a. And we'll call its equation L of x, L for linear, of course. And this is the equation. And right, what makes this thing special? Well, it passes through our point, a comma f of a. That's why you're seeing this a here and f of a. That's just really the y coordinate. And then the slope of this line is what? Well, it's equal to the slope of our curve at the point x equals a. So in other words, right, the slope of your linear approximation is just the derivative of your function evaluated at a. All right. And so now let's go ahead and say we do zoom in near this point a comma f of a, right? We're going to start to see something like this, right? If I zoom in closer and closer, okay, this gap between our red tangent line and our yellow curve is going to decrease, okay? So another way to say that is that the function values for f of x will be very close to the function values for your linear approximation as long as you don't deviate too far away from this point x equals a. Okay, and we can even say a little bit more than that. So let's say we do deviate a little bit away. So I'll call that deviation amount in x, I'll call that dx. So let's say I increase x by dx, right? Well then my function value will presumably change some amount, and I'll call that true change in my y value. I'll call that delta y. And then I could also consider the change along the red tangent line. Okay, and I'll call that dy, right? Now this will be the approximate change in y, also known as the differential change in y. And a reason why you'd want to call this this change dy is that, look, the ratio of dy to dx would be what? Oh, that would just be the slope of the red line, which is equal to the derivative of our function, right? So you know that this notation dy dx is commonly used for the derivative, so this is a good choice for calling this the approximate change. Okay, and down here what I'm saying is the differential of our function f, right? This is the dy change along our tangent. And what is it equal to? Well, it's simply the derivative at a, so in other words, the slope of that red line times the run, right? If you take the slope times the run of any line, you're just going to get the rise along that line. And so we have this equation right here. And then rephrasing this statement that f of x is approximately L of x, I can say that in terms of differentials as what? Well, the true change in my function is going to be approximately equal to this differential change, dy, as long as my deviation, my dx here, is small, okay? Okay, so we are now going to do all of this stuff for functions of multiple variables, but instead of, say, curves, we're going to be looking at surfaces, and instead of tangent lines, we'll be looking at tangent planes. But all of these conceptual ideas will carry over directly. All right, so we'll start that all in the next video. See you there.